Welcome back to the deep dive, where we cut through the noise and get to the core of what's truly important. Today, we're tackling a big question in the world of AI. Why do these incredibly smart large language models, LLMs, sometimes feel like they have a bad memory? You've probably marveled at their ability to write code, compose poetry, or answer complex questions. They seem like brilliant minds, don't they? But then you hit that familiar wall. They forget what you said maybe a few turns ago, or they don't quite retain your preferences over time. It's a bit like talking to someone super insightful who just, well, can't remember your last conversation.
That observation really hits on a core challenge.
Mm.
Today's LLMs largely rely on static internal knowledge or a very limited temporary context window.
Context window.
Think of that window as a kind of small notepad they could use for a short conversation. But once it's full, they start forgetting the earlier notes.
Right.
This really restricts their ability to, learn and adapt over long periods, track your persistent preferences, or keep their knowledge consistent. And while Retrieval-Augmented Generation, or AGI, helps by pulling in outside info.
RG, yeah, we hear a lot about that.
We do. But our sources note it often acts more like a quick lookup. It's often a stateless solution, meaning it doesn't have proper lifecycle control. It's not a deeply integrated system that truly helps the AI remember and adapt long term.
So if that's the problem, this brilliant mind with short-term memory, what's the breakthrough solution? We're diving deep into an innovative answer called MemOS. That stands for Memory Operating System for AI System.
A MemOS?
Yeah. Our mission in this deep dive is to explore how MemOS completely redefines memory. It treats memory as a fully manageable system resource, kind of like your computer's operating system manages its CPU or RAM. We'll unify different types of AI memory, explore the critical new capabilities it brings to LLMs, and uncover how it aims to transform them into continuously evolving intelligent agents. Agents that can truly remember and adapt. Okay, let's unpack this foundational challenge, though. Why do these incredibly powerful LLMs struggle with memory in the first place? It seems a bit counterintuitive given how much they know.
It does, doesn't it? The core limitation comes from how LLMs are built. Despite having immense knowledge encoded within them, they struggle with what's called long-range dependency modeling.
Long-range dependency modeling.
Right. It means in a lengthy conversation, the model might lose track of your specific instructions or maybe a preferred writing style you mentioned much earlier. It often reverts to its default way of doing things.
Ah,
This happens because their context windows, that temporary notepad we mentioned, are limited. And processing huge amounts of information within that window becomes computationally very expensive.
so it's not just forgetting a single detail, it's about losing the thread of the conversation or that consistent personalization. And I guess that also impacts their ability to keep up with how fast the world changes.
Definitely. Real-world knowledge is constantly evolving. Think about new scientific discoveries or shifts in legal rules. But LLMs, with their largely fixed knowledge base, they struggle to integrate these timely updates.
How so?
Well, it's difficult for them to retire obsolete facts or prioritize reliable ones without expensive and, time-consuming retraining. Similarly, for personalization, LMs often don't create lasting memory traces. Each new session can feel like you're starting from scratch, completely ignoring all the preferences you've carefully taught it before.
And it gets even trickier when you're using different AI tools, right? It can feel like each one is its own separate little world.
It certainly can feel that way. Our sources highlight this as the memory islands problem. Valuable information or your user history often becomes isolated within individual platforms.
Memory islands.
Yeah. The insights you gain or the context you build in one AI tool, say ChatGPT, can't easily transfer or be reused in another, like maybe a coding assistant like Cursor.
Right, you have to start over.
You do. This forces you to constantly rebuild that context, leading to inefficiency and just a fragmented experience. It's a systemic issue that goes beyond just the LLM itself. It touches on how knowledge is managed across different tools.
So MEMA steps in here to tackle these systemic memory issues. The core idea sounds pretty revolutionary, treating memory not as some hidden thing, but as a dedicated, explicit system resource. How does changing the structure like that actually boost an LLM's capabilities?
That's really the heart of it. MemOS redefines memory. It transforms it from something sort of latent, hidden inside the model, to an explicit first-class resource that is centrally managed. Like I said, picture your computer's operating system managing its CPU or RAM. It's that level of management. This fundamental shift provides a unified framework for organizing, scheduling, and evolving memory across different tasks, users, even multiple AI agents. It's a big step towards making AI truly adaptive.
That structural change sounds like it unlocks entirely new ways of doing things. What are the key capabilities that this system-level approach actually brings to the table?
Well, there are three foundational capabilities highlighted. The first is controllability.
Controllability.
Right. MemOS offers full lifecycle management for memory units,
Yep.
from their creation and activation, all the way to their fusion and eventual disposal if needed. Include multi-level permission controls and smart activation strategies that understand the context. This ensures safety and clear tracking, which is especially important in complex setups with multiple tasks or users.
So you can control what is remembered, when, and by which part of the system.
hmm For example, specific user preferences can be tied to particular AI agents and even set to automatically expire when they are no longer relevant. This gives you very granular control over what an AI remembers and for how long.
Okay, that's controllability. The second one you mentioned, plasticity, sounds like it's all about flexibility.
It is. Plasticity refers to memory's ability to be restructured and moved fluidly across different tasks and roles. MemOS allows for memory to be sliced or tagged and organized into hierarchies.
Sliced and tagged, how does that help?
It means the system can activate different memory views tailored to specific objectives. Or it can dynamically update memory associations as an AI's role shifts. For instance, an AI acting as a legal advisor might load one set of memories for drafting a contract and then a completely different set for researching litigation cases.
So it's not just remembering, but remembering how to remember for different jobs. And the third capability, evolvability. That suggests continuous self-improvement.
You've got it. Evolvability highlights MemOS's capacity for dynamic transitions and unified scheduling among all the different memory types. This means, for instance, frequently used user-defined rules, initially stored perhaps as simple text, can be converted into activation memory for faster access.
Faster access.
Yeah. Or, if they become stable, long-term knowledge, they can even be compressed into a more efficient parametric form, basically integrated directly into the model's core knowledge. This cross-memory adaptation provides a really robust foundation for integrating knowledge and enabling autonomous learning. It lets LLMs continuously adapt and improve over time.
It's clear MemOS treats memory as something much more dynamic than we're used to. Let's dig into the actual building blocks that make this work. I read about something called a MemCube. What exactly is this?
The Memory-Cube, or MemCube, yes. It's the core standardized encapsulation unit within MemOS. Think of it as the standard container. Its purpose is to unify the management of all these diverse memory resources.
Why is unification so important here?
Well, because LLM memory is really varied, right? You've got knowledge baked into the model's parameters. You have intermediate processing states. You have external text fragments retrieved from somewhere. The MemCube provides a consistent way to handle all of it.
Okay, a standard container. And what's inside each MemCube?
Each MemCube has two essential parts. First, the memory payload. That's the actual content. It could be anything from a retrieved piece of text to a user instruction, or even a specific adjustment for the AI model's internal state, its activation memory.
The content itself. And the second part?
The second is the metadata. This is where the real intelligence of the memory management happens. It provides the, let's say, DNA for that piece of memory. It contains crucial info like descriptive identifiers. Where did this memory come from? When was it created? What type of information is it? Things like that. Then there are governance attributes who can access it. How long should it last? What's its priority? And finally, behavioral usage indicators. How often is it accessed? How recently? This metadata allows memory to be truly intelligent. It enables its dynamic evolution and flexible use across the system.
So the MemCube uses this payload and metadata to unify all these different kinds of memory. What are the three main memory types that Memo explicitly models and brings together using this structure?
The first is plaintext memory. This is your explicit external knowledge, things like retrieved documents from RAG, structured data graphs, or maybe prompt templates. It's easily editable and can be stored independently.
Which makes it good for updates.
Right, it's great for rapid knowledge updates and user personalization. Memo integrates this deeply, allowing it to interact with the other memory types and even evolve into faster forms if it's used a lot.
Then there's activation memory. That sounds more like what's happening right now in the moment of processing.
Yes, exactly. Activation memory comprises those intermediate states generated during the AI's thinking process. It's like a short-term working memory, often referred to technically as the KV cache in hidden states.
Okay.
It's short-term, dynamically activated, and it plays a vital role in maintaining contextual coherence, keeping the conversation thread, and allowing for those instant responses you expect. MemOS provides unified scheduling and lifecycle management for this type too, meaning frequently used patterns here can form instant memory paths for very low latency access.
And finally, parameter memory. That's what we often think of as the LLM's core knowledge base, right?
That's it. Parameter memory is the knowledge and capabilities deeply encoded in the model's fixed weights. It's the main repository of long-term semantic knowledge. MemOS allows this to be enhanced in a modular way, maybe through lightweight fine-tuning. But crucially, MemOS intelligently links this parameter memory with the plaintext and activation memories.
How does that linking work?
Well, it enables capabilities like distilling frequently used plaintext knowledge into a more efficient parametric form over time. Or, conversely, using new plaintext to effectively update or override outdated parameter memory. It creates a truly unified and, importantly, evolvable knowledge space for the AI.
This unified system sounds very sophisticated. The sources describe a modular, three-layered architecture. Could you walk us through how these layers actually work together to manage the memory flow?
Certainly, MemOS operates through this modular structure. There's an interface layer, an operation layer, and an infrastructure layer. Each has distinct jobs, but they work together seamlessly. The interface layer is the entry point. It's where users or other systems interact with memos. It features a mem reader that parses natural language inputs, what you type or say, into structured memory calls, figuring out your intent and the relevant memory needed.
So it understands the request.
Yes. It also provides a unified memory API, a set of standard commands for tasks like creating memory, updating it, retrieving it, even auditing it. Think of it as the main communication hub.
Okay, the interface layer translates user needs into memory actions. What about the central brain, the operation layer?
The operation layer is the central control hub. This is where the core logic resides. It has a mem operator that organizes memory content using those tags and links we discussed, supporting smart hybrid retrieval. Then there's the mem scheduler. This acts as the central dispatcher. It dynamically transforms and loads memory units based on what the task needs and how often particular memories are accessed, always optimizing for speed and relevance.
And there was something about lifecycle management.
Right. Crucially, its mem lifecycle module manages the state of each memory unit. Is it newly generated? Is it active? Has it been merged with other memories? Or archived, maybe even expired? This module supports that semantic evolution we talked about, and it even includes a time machine capability.
A time machine for memory.
Yeah, for rolling back memory states, potentially for debugging, recovery, or even exploring alternative scenarios based on past information.
Interesting. Okay, and finally, what underpins all of this? The infrastructure layer.
The infrastructure layer forms a robust foundation. It handles memory storage, security, and migration. Its mem governance component enforces access rules, those lifecycle policies like time to live, and ensures auditability for data privacy and compliance.
Governance is key.
Absolutely. Then the Mem Vault acts as the central storage and routing system, interfacing with various back-end databases where the memory actually lives. This layer also provides tools MemLoader and MemDumper for seamless memory migration across different platforms. And MemStore enables controlled publishing and sharing of memory units among multiple AI agents or systems. These layers work together, using the MemCube as the standard unit, ensuring a structured, traceable, and governable memory system.
All this architectural work, it must lead to state-of-the-art better than others.
It shows particular advantages in challenging scenarios, like multi-hop reasoning, where you need to connect multiple pieces of information, and temporal reasoning, understanding time. It outperformed strong baselines like MemMem, LangMem, ZEP, and even OpenAI memory in LLM judge scores, which is a common way to evaluate these systems.
That's impressive for raw performance.
Yeah.
But what about efficiency? Running these large models, it can be quite costly, right?
That's a huge point. Beyond just performance, MemOS demonstrates significant efficiency gains. It not only matches or surpasses the performance of systems that load the entire dialogue history into the context window.
Your full context approach.
Right. It does that, but with substantially lower latency. A key factor here is its KV-based memory acceleration strategy. This leads to really dramatic reductions in time to first token. That's how quickly the AI starts responding.
How much reduction are we talking?
Up to 91.4% for larger models under specific conditions, like long contexts but short queries. And critically, this speedup happens without altering the quality or the semantic meaning of the output. So you get much faster responses without sacrificing accuracy.
That sounds like a huge win for user experience. Beyond just the performance numbers, how does MemOS fundamentally change how AI systems can actually be built and used? This seems to open up new paradigms.
It really does seem to. One innovative concept highlighted is paid memory as modular installables. This is fascinating. It allows domain experts to essentially publish their structured experiential memories, think specialized knowledge, via the Mem store.
Like a knowledge plugin?
Almost exactly. Users or maybe enterprise AI agents can then install and invoke these memories through a standardized interface. Access is controlled by that Mem governance layer we talked about. This drastically lowers the barrier to accessing specialized knowledge. It makes expert insights readily available without needing complex custom integrations.
So it's kind of like an app store, but for specialized AI memories.
That's a great analogy. And I imagine it also simplifies things for developers or even regular users interacting with memory.
Yes, that leads directly to the second innovation mentioned, painless memory management. MemOS abstracts away a lot of the complex, low-level memory handling, things like manually managing vector indexes or dealing with that KV cache.
Stuff most users don't want to think about.
Right.
Instead, you or developer can flexibly read, write, combine, or replace memory blocks on demand using high-level memory API calls. The example given is a legal assistant AI. It could dynamically load different memory sets for distinct phases of a contract review. First loading contract template memory for the basic layout, then switching to risk clause case logs for comparison against past issues. The system handles all the underlying complexity.
This all sounds incredibly practical. How does MemOS directly impact the common frustrations we, experience with LLMs in real-world applications day to day?
It addresses several critical areas directly. First, it tackles multi-turn dialogue and cross-task continuity. It aims to solve that common memory loss problem in long conversations. It does this by extracting key information into structured conversation memory units and linking them to ongoing tasks. This ensures a consistent understanding over time.
And across tasks.
Yes, it also enables memory reuse across different tasks. So, for example, details you entered for an auto-form filling task could potentially be retained and used for a subsequent visa application, meaning you don't have to keep re-entering the same information.
Okay, that's useful. What about the constant struggle with keeping the AI up to date with new information, like new regulations or discoveries?
MemOS directly supports knowledge evolution and continuous update. Because it treats knowledge as dynamic, lifecycle-governed memory, it allows LLMs to adapt to continuously evolving real-world information like updated clinical guidelines or new financial regulations without needing that expensive full retraining process.
So the model stays current.
That's the goal. It helps ensure models remain up-to-date and reliable. A medical authority, for instance, could release updated guidelines as explicit memory blocks. MemOS could then tag these as trusted sources, ensuring the AI prioritizes the latest, validated information.
This also sounds like it would significantly enhance personalization, making the AI feel more tailored to the individual user.
It absolutely does. MemOS enables personalization and multi-role modeling. It provides system-level support for identity-aware memory and role-based behavior. Each user can have their own dedicated memory space.
In different roles.
Yes, an AI could even maintain distinct personas, for example, acting as a helpful parent for home-related tasks and a professional manager for reviewing work contracts, dynamically loading the appropriate memory based on the interaction context. Your long-term interaction patterns could be encoded into personal memory units, ensuring the AI's behavior feels consistent and really tailored to you over time.
And finally, that memory islands problem you mentioned earlier, where knowledge gets trapped inside one app or platform, does MemOS help break those down?
It aims to, yes, it enables cross-platform memory migration. By standardizing how memory is represented and the protocols used to access it, MemOS effectively breaks down those memory silos. Memory blocks become portable.
Portal how?
They can move across diverse environments, from maybe your mobile device to cloud services, ensuring continuous knowledge and a consistent user experience wherever you interact with the AI. The example given is your family travel preference memory, built maybe through a mobile assistant, could be selectively moved or accessed by a corporate travel planning agent running on your desktop. This ensures consistent and efficient decision-making across different platforms.
Wow. This deep dive into MemOS has certainly revealed what sounds like a really significant leap for large language models, equipping them with this sophisticated, explicit, and perhaps most importantly, evolvable memory system. It really moves them beyond their current static or kind of transient capabilities towards becoming, well, more truly intelligent agents that are capable of learning and adapting over time.
It's a fundamental shift, it seems, in how we approach building AI memory systems.
So here's a final thought for you, our listener. Considering how crucial effective memory is for human intelligence, how might this fundamental shift, treating memory as a fully managed operating system resource within AI, how might that redefine the long-term potential, the future capabilities of artificial general intelligence itself?